You guys might have kind of noticed this, but the first part of the course is pretty much sort of like one theme. We talk about MapReduce for a long time. We talk about streaming and parallelization for a long time. And the last part of the course, really I kind of skip around to a whole bunch of different things. So today I'm going to talk about scaling up of a particular kind of learning algorithm, semi-supervised learning algorithm, learning on graphs. This ties into stuff we've been talking about before. So let me start out by just talking about semi-supervised learning. So I always talk about this when I do 601, but not everyone does. How many people know what semi-supervised learning is? How many people haven't really heard the term before? Not sure what it is? Yeah, okay. All right, so this will be new to some of you, old to some of you. So the basic idea is, normally in learning, we start off with some labeled examples, and we learn, let's say, a classifier. Let's talk about classifier learning here. So here, we have some labeled examples, but we also have some unlabeled examples. And you can see why this might be useful, right? So if we're learning to like classify images by the objects in those images, it might be good to have a bunch of images that are labeled with, this is a walrus, this is a penguin, this is a Yorkshire Terrier, right? This is, I don't know, a plane. But it also might be useful. One resource that I could easily get would be loads and loads of images that exist but don't have labels. And it's the same thing if we're looking at classifying email as spam versus not spam. I can certainly find some spam email. I can certainly get some non-spam email. But one thing that would be relatively easy to collect is all my email, right? I can just use IMAP and pull it all out of Gmail, and I have more email than anybody would ever want to look at, trust me. Okay, so it's often possible and inexpensive to get a big pool of unlabeled examples. So the question is, how can that help you? So there are a couple of things that you could obviously do. You could just not use the unlabeled examples. All right. Or another possibility is you could use the unlabeled examples and just treat it as an unsupervised learning problem first. Okay, so you could take all the examples, the labeled examples and the unlabeled examples, and run your favorite clustering algorithm. So you find these clusters, and then each cluster would get labeled, since there's some labeled examples in this mix, would get labeled with maybe the most frequent label in that cluster. Okay, so that would be another possibility. So in the first case, you're obviously not making much use of the unlabeled examples. In the second case, you're making some use of the labeled examples, but it doesn't seem to be like an optimal use, right? So the question is, is there something you can do that uses the labeled examples and the unlabeled examples, systematically together, in some kind of joint way? So here's a little bit of an intuition as to why semi-supervised learning might be helpful. So let's imagine. So these pluses aren't labels, they're just what the character I used for points. Let's imagine I've got a bunch of points. So if you wanted to cluster these, you might do something like this. It's like, well, those are kind of naturally two clusters. But even though I made this case pretty easy, there are lots of situations where there isn't one natural clustering. So here's another set of objects in slightly more than 2 dimensions. You may have seen these objects before. And there might be, if I went and asked people in this room to cluster them, there might be a couple of different possibilities. So you might cluster them into kind of the main characters, Homer Simpson and his family. Or you might say, well, we've got boys and girls, right? Or maybe you've got children and adults, right? I mean, there's all sorts of possibilities, right? So clustering is kind of a subjective task. It's not immediately obvious what the right clustering is, okay? And it's very easy to have a situation where there's some clusters that are intended and some that are not intended. So maybe this is kind of one possible clustering, but maybe not the most obvious one, right? So it might be that if you ran a clustering algorithm, you wouldn't get this, even though that's what you'd really like to see. Or maybe it's the other way around, right? Maybe your clustering algorithm likes this, but really you'd like to see the first one I showed you, right? So clustering is unconstrained. So if you just cluster, it may not give you what you want. And then even if I'm sort of classifying things by the majority label, maybe this thing will all have the same label, but maybe this one's mixed, so I get kind of a noisy result. It's also the case that classification learning is unconstrained. So if we've got a lot of examples, we'll probably, and we choose a restricted classifier like a linear classifier, we'll probably get the same result or similar results each time, right? So this would be kind of a reasonable way of classifying this data if I knew all the labels, red and green, all right? If I just have a few things that are labeled, then there might be a bunch of different ways I can classify the data. So maybe this separation is just as good as the other separation. So if I have a few labels, then classification is also kind of unconstrained, right? And again, it might not give you what you want. So remember here, probably what we want is something like this. And this separating hyperplane doesn't really give you that. So the idea is in semi-supervised learning is to do a little bit of both, right? So we're going to A, look at these, the natural clusters, and B, look at the labels, and try and come up with something that's consistent with both of those, right? And exclude things that maybe are reasonable clusterings, but are not consistent with the labels. So that's the basic idea and intuition, okay? So this is kind of what we're going after, okay? So just to make this concrete, here's a semi-supervised learning system that, so this is a research project that Tom Mitchell and I and a bunch of other people have looked at for a while. So what does it do? What it does is it classifies two types of objects. It classifies named entities that it's found on the web, and it also classifies pairs of named entities. So named entities are classified into all sorts of things like sport events or machine learning algorithms or religions and so on and so forth, okay? So these are all things that, that Null thinks are religions, okay? Chippewa mythology might be a little bit of a boundary case. And along with this, there are a couple of different properties. So one is confidence, and there's also whether this was a seed that was given by a human being or whether it was learned. So Null is sort of an iterative learner, so there's also an iteration number, and it is kind of slow. So there's a date when this was learned. So it's been sort of like running for years, kind of bootstrapping these things. Or another example, it's got a list of colors somewhere. Okay. So it thinks all these things are colors. And it also has, in addition to objects, it has relationships, okay? Again, there's like hundreds of different relationships, but, this would be a list of relationships held by certain entities. So Benazir Bhutto, Prime Minister, or another Prime Minister, David Cameron, okay? And the end result is that you have a lot of information about the individual entities and places. So if we look at how Null works under the hood, what you do is you start out by knowing about these categories and these relations. You understand a little bit about the relationships between these categories. So, for example, we know that Prime Minister is a political office, and David Cameron and a politician is a kind of person. So there's subset relationships, and there's also relationships about which things are mutually orthogonal. So a person can't be the same as a political office, or an organization can't be the same as a single person, and so on. Then there's also several different classifiers. The first one is kind of the easiest one to describe, which is basically you look at features which are where these named entities appear, where these entities appear. So if we've got blank was elected party leader, blank became Tory leader, politicians see blank, right? Conservatives like blank, other persons named blank. So some of these are good indicators that somebody is I guess the category here is person in Europe. Some of them are less good indicators. So those are basically features, and you kind of learn which features are important. There are other sorts of features that get learned. So for example, one thing it learns is it learns to find, tables and identify those tables with different types. So it's figured out how to parse this table in Wikipedia, right? And somewhere it knows that being in that table correlates with being a politician. It's not big surprising. This is, category of politicians. Okay. But it figured that out on its own. So that's cool. So this is semi-supervised learning. Yeah, question?
Does this system support natural language query? Like, for example, can I search who is the 20th president of America?
No, there's not a natural language query interface to know. It'll be cool. But, yeah. Okay. So this is sort of the sort of thing you can do. So in Nell, there's several hundred different categories, and there's several hundred relations. And putting that together, that set of categories and relations, was a big task. There's multiple learners for each one. And there are also examples for each one of those categories and relations. But the number of examples is very small. It's like on the order of like 10 or 20. So there's a relatively small amount of labeling involved in training Nell. So it's an example of semi-supervised learning. Because it's using a lot of unlabeled data. So how do you do semi-supervised learning? So I'm not going to give you a good survey of this. What I'm going to do instead is I'm going to dive into one particular method or one particular family of methods, and I'll talk a lot about those. So these are methods that are pretty different from the kind of supervised learning techniques we've talked about. They're much more closely connected with the kind of graph processing that we talked about earlier this year, talking about how we scale up PageRank and so on. So these are basically ways in which you formulate semi-supervised learning, which is often on pretty large data sets, to operations you do on a graph. So that's basically, all I'm going to be. Someone should really mention when I don't bother to put things in, like, display mode. Okay. So this is what I'm going to be talking about the next hour, I guess. Okay. So let's start out with one particular algorithm. Okay. So here's the basic idea. Let's imagine I've got some data. So here, let's say my examples are, this is the MNIST data, so these are all like handwritten digits. All right. And I'm going to assume that I've got a lot of these digits, but only a few of them are labeled. Okay. So I've got many unlabeled examples, only a few labeled examples. So these ones with the blue here have got labels. So that's a 9, this is a 1, that's a 0. Okay. What I'm going to do is I'm going to take these unlabeled examples and connect them up in a graph. So I'll have a weight between every an image and its most similar images. So this guy's connected to 2 things. Right, this guy's connected to, I guess, also 2 things. But this one happens to be connected to like 3 nearest neighbors. So maybe what we're seeing here is everything like within some distance is connected. So there's some variance as to how you might want to do this, but basically the idea is we take everything, we connect it to things that are highly similar to it, and this gives you this graph. So often these edges will be weighted. So the similarity score between 2 things will be a weight on that edge. All right, and the basic principle we have is that if you have points that are nearby in a graph, then they should have a similar label. Okay, so we know a few of these labels, and the ones that are immediately close to those, we can say, with some degree of confidence, well, they should probably have the same label as this thing that they're very close to. That's kind of the nearest neighbor principle, right? And then if I know that this thing is probably a 2, then this thing is also close to that 2, so it's also probably a 2, right? Of course, I've got some things that are close to multiple different things, so I've got to figure out how to break those ties, right? So we need some sort of algorithm that tells us how we're going to take these labels and propagate that information through the graph, all right? So possibly the simplest idea is this following one, okay? So just imagine for now I just have 2 labels, 1 and 0, so it's just a 2-class problem. So maybe I'm like classifying 2s versus everything else, okay? So I've got a label for every node in this graph. So yi is the label on node I. And that label can be either 1 or 0, or just relaxing things anywhere in between, right? So we can have some sort of fractional decision as to what its weight is. So the things that I know the labels for, like I know this is a 2, I know that's not a 2. So I know this weight should be 1, and I know this weight should be 0. What would be like a reasonable goal to have, right? So what I want to do is I want to find labels. I want to find scores for each of these internal nodes that minimize some loss. So one plausible loss is this one. So whenever there's an edge, I want the things that are connected by that edge to have the same label or a similar label. Okay, so I'm going to have a penalty, on every edge, which is the square of the difference between the source and destination of that edge. So if I had two things where they're both labeled 1, in other words, they're in the category 2. I'm sorry, that's confusing, right? In the positive category, then they would have, a loss of 0, so that would be fine. If they were labeled 0 and 0, that'd be fine. If one was labeled 1 and the other one was labeled 0, that would be bad, right? So you get some penalty for that. Okay, so we can just basically take that penalty and sum it up across all the edges, and we add an additional constraint that we sort of have to match the seeds, all right? And this gives us a loss, all right? So minimizing the loss isn't a learning problem. We're not setting parameters. Instead, we're just figuring out what the internal labels of this graph are, okay? So these blue things, like I said, are the observed labels. So in the case where it was binary, then y could just be 0 or 1. If I've got 10 labels, then the natural thing to do here is to make y be a vector. So it could be a length 10 vector, and it'll be 1, 0, 0, 0 if the first class is true, and 0, 1, 0, 0, 0 if the second class is true, and so on and so forth. So that would be for the seeds. And then I could write a similar function as this, right? So the squared difference would be presumably something like, squared Euclidean distance. Yeah?
What is y, the other nodes to which we are comparing this node?
So what is the other y? So we're looking at an edge, okay? So we're looking at each edge in the graph. And for every edge, there's a penalty if you give the things at that edge different weight, different labels.
What do y represent the label?
Y represents the label on a node, okay? I'm sorry?
We don't have labels for those nodes.
We have labels for a few of them, okay? So for some of these y's, this is known, okay? For some of them, it's not known. We've got to come up with a y for every node, okay? So we're looking at scoring a vector of nodes, okay? So this would or a vector of y's. So this would be one class assignment for every node, okay? So I haven't told you how to get there yet, but what we want to optimize is we want to minimize the energy, okay? So the energy is high if you have two things that are connected that disagree, okay? So I mean, as long as there's some path from everything to everything else, as long as the graph is connected, and as long as you have more than one different label, there's going to be some non-zero energy. You can't like put this energy down to 0.
And how did we choose to how many neighbors a particular node should be connected with? How did we decide that?
So that's kind of that's a parameter of the algorithm that you've got to figure out. So like when you're doing k nearest neighbor, you have to figure out what k is. You also have to figure out what the distance metric is. So here we have to figure out a distance metric. We have to figure out k. There are some other little details like this is kind of assuming that these edges are undirected. If they're directed, then we want a slightly different formulation. But if they're undirected, then this could be this guy could be one of the k nearest neighbors of this guy, and this guy might not be one of the k nearest neighbors of this guy. Right? This guy is sort of sitting in a dense space, and this is in some less unpopulated space. So you may want to take the k nearest neighbor graph and make it symmetric. So there are a bunch of questions. How do you construct this graph? That's a great question. What sort of distance metric do you use? How do you formulate the loss function? And of course, how do you actually solve the loss function? So this sounds like a hard problem because I've got to assign a real number to every node in this graph. Okay, even if they're just two classes, right? You know, and they're n nodes, I've got, order 2 to the n real numbers, right? So there's a problem in how you do it. But it turns out there's a simple way of doing this. So if we take this and differentiate, we can basically come up with a gradient. In the gradient, what we're basically trying to do is we're trying to make the value at each node the weighted average of its neighbors' weights. Okay? So if we look at a little area like this one, okay, we can start out, the seeds will have a value. All right, let's say 2 is my positive class, so this is a value of 1, this has a value of 0. Maybe all the other seeds have a known value of 0, and then these other ones have like an unknown value. So we can start with some random starting point, okay? And we do a gradient update, and what we're basically doing in our gradient update is we're moving that node, each node toward the weighted average of its neighbors. And then we basically will repeat that. So here's the algorithm, okay? So every seed example, we're basically we have a matrix here, which basically says there's one row for every node, I, and there's one column for every class, all right? And we'll put a 1 in that if, as a seed, if that has a known value of C, okay? And otherwise, we'll just set them to be 0, okay? And then the next step is what I'm going to do is I'll iteratively do the following. And usually this converges pretty quickly. And it often overfits if you let it run too long. So really, you would do this about 5 or 10 iterations, approximately. Not 30 iterations, not 10,000 iterations, not 1 iteration. Something like 5 or 10. And what you do is you replace every, you can basically construct a new copy of this matrix where each value is the weighted average of its neighbors. Okay? Right? And then after you do that, you renormalize. Okay. So I guess I shouldn't have made all those things that were non-seed 0. I guess I should have made them uniform probability or something. All right, so we'll renormalize this, and then we'll repeat. Okay? But before I repeat, I'm basically going to reset all the seeds to their known value. Okay? So this is basically the algorithm. So you basically replace each node's value with respect to each class with the weighted average of its neighbors' values, right? So you're looking at all the things it's connected to, looking at their value, taking a weighted sum of that, and that's the score you'll get for each class, and then you normalize. So a very simple algorithm, okay? And it turns out to work okay. This family of techniques is called label propagation. So here's some experiments. This is using these digits. We're comparing it with support vector machines, I think with a quadratic kernel, although I don't remember the experiments all that well. So here are a couple of variants of the label propagation algorithm. So one is using cosine distance on these digits, these images. Another one is using another distance metric called Jensen-Shannon. So they behave kind of similarly, and I guess the key thing is when there's a relatively small number of labeled examples, they do a lot better. So the sweet spot here is you've got a graph, we've got good connectivity, and we don't have too many labeled examples. So is it kind of clear what's going on here? There were a bunch of questions earlier on. Do we know what we're doing? Okay.
Can you go to the previous slide?
Sure.
What's the B value for the non-seeds?
Okay, starting off here, you mean? For the non-seeds, we'll just make it a uniform distribution, okay? It doesn't really matter. This is going to converge relatively quickly, and it's a convex problem. So it doesn't matter too much what you start off with, but let's start off with like a uniform weight over all the different classes, okay? And at the end of the day, after I converge, okay, this property will hold, okay? So at the end of the day, we'll get a fixed point of this, all right? And in that fixed point, after we've converged, then the score for every node will be the average of its neighbors. So this is sometimes called the harmonic fields algorithm because you end up with a harmonic function, an average of the neighbors. Okay. So this is the basic idea. So Nell uses something a lot like this, okay, except the graph is a little bit different. So null, there's basically 2 nodes in the graph, and this is one of the learners in null. So this is the couple pattern learner. So you have entities, which are basically just noun phrases that you find in text. And then you have features, which are just little context, a few words around that noun phrase, right? And there's an edge, which basically connects a entity if it appears in that context. Okay, so you might see mayor of Pittsburgh, mayor of Seattle, mayor of Cupertino. You might see live in Seattle, live in Paris. So all these things are connected, right? Then there are other things that are also connected to these same patterns, okay? So the problem, I guess, so here, what you'd like to see happen, we start off with some examples, all right? And we've got these things which are basically features of those examples, all right? And just to break it down a little bit more, what we're really going to see is we're going to see something like this. We've got individual features connected to individual entities. So these are, let's say, my 3 seeds. These are the features that appear with those seeds, all right? So what we're going to do is we're going to take the weights for these entities. Let's say we pin these to 1. These are seeds. All right, and then we look at the average. Then we do our label propagation, so we get some weights on these features, which are also nodes in the graph. All right, then we look at things that are connected to those features. So these would be other things which appear in the same patterns. So you can be a mayor of San Francisco or Austin, so that might appear. You can also live in Austin or San Francisco. You can also live in denial. A lot of us last week or so, it's kind of been popular. So it's not the case that everything in here will be correct, all right? But we'll do some sort of label propagation, and what's intended here is this grayness is sort of the score, right? So the seeds are really strong, and then as we get further away from those, we'll get lower and lower values with respect to this label, all right? And one question is, so these are basically things that are close to the seeds, and these are things far from the seeds, all right? And then information from other categories tells us, how far to go. So this is why null has so many different categories. If you're just trying to figure out where the boundaries of this would be, where this might be hard, but if someone gives you some other categories or other seeds, like we know arrogance is a character trait, okay, then we would get some links between that arrogance and these other things. So that would help you set up a boundary between these, all right? So this is the basic idea. Okay. So the big difference here is the format of the graph. So instead of basically having entities and nearest neighbors between the entities, we've got entities and features of the entities. That actually is sort of a substantive difference. Practically, here's kind of my kind of take on it. If you're careful in sort of choosing your distance metric and choosing the parameters of your nearest neighbor graph, you can usually do better than you can with this sort of instance feature graph. So this is not going to be as good in terms of classification accuracy most of the time, but it's much cheaper to build. Okay, so usually you have this basically. You don't have the nearest neighbor graph. So constructing the nearest neighbor graph can be an expensive thing to do. It's basically sort of like a soft join operation. So often, it's much less expensive to do this sort of semi-supervised learning in practice. So that's the basic idea behind semi-supervised learning. What I'm going to do over the next few minutes is kind of talk about different variants and present some more experimental results and so on. But just to kind of give you a little bit of an overview of what kind of some of the technical problems are, right? So one question is, how much unlabeled data do you want, and how much do you use it? In the energy function I just gave you, you're looking just basically sort of at smoothness, right? You're looking at how much difference there is between the weights in the graph. And there's a hard constraint that you match the seed labels, all right? In a lot of situations, it's a little bit more flexible. So there's some penalty for how some penalty for not using the labeled data, and there's some penalty for not giving consistent predictions on the unlabeled data, okay? So often the energy function, the score that you set up is basically a sum of two components. One which is basically how well you did on the labeled data, the other one is how well you did on the unlabeled data. So if I give you like 10 examples per class, and you've got 100 classes, so you've got 1,000 labeled examples, and then I give you a million unlabeled examples, that's one way of balancing this, right? And if I give you 100 million unlabeled examples, you've just made those unlabeled examples much more important. So there's kind of a trade-off, right? If you get more and more unlabeled examples, eventually this term of your loss function just starts to dominate, and you start ignoring the labels. So that's often a problem. So there's often some, decision you have to make about balancing those things, sort of like choosing a regularizer. Another thing that's often very commonly done is to put a little bit of extra information into the semi-supervised learning algorithm. So something might be like, you might get things like the relative frequency of the classes, so you might be somehow biasing things to give you, a partition that's roughly 50-50 of if you've got a two-class problem, for example. So these are some of the issues that in practice you kind of have to deal with, and so this is kind of why semi-supervised learning is often a little bit fiddly compared to classification learning. So if you start off with a labeled data set of a reasonable size and you run random forests on it, then high probability it's going to sort of work. But if you try and use a semi-supervised learning algorithm, you may be looking at a bit of time sort of fiddling around with it before it really works. Okay. So questions before I move on? All right. So I'm going to give some more algorithms. Maybe this will make things better, or maybe it won't. This is an algorithm that you guys basically could already implement, or more or less you already have implemented, even for pretty large examples, large graphs. So, this was work by one of my former students, Frank Lin. What we were looking at is we were looking at classifying data that was naturally in graphs. So you guys are looking at this data set, which is blog data, and or last assignment you were looking at this. You were looking at sort of trying to find natural partitions of that blog data. So that's a case where we actually really do know the labels, and there's also some structure. And there are lots of data sets that are similar to that. So we might have websites or newspapers that are kind of linked by political affiliation. We might have like technical papers that are linked by citation information. So there are lots of cases where you have entities that have some sort of direct relationship between entities. So this is the sort of data we're looking at. It's not quite the same as data where you've got entities linked by a nearest neighbor relationship only, but very similar technically. And a lot of these techniques work also for that sort of data. So what was Frank's algorithm? So a similar sort of thing. So for every class, what we're going to do is we're going to go through all the seeds, the labeled instances, all right? What we're going to do is we're going to set up a vector for each class, all right, which is uniform over all the positive examples of that class, okay? So in Frank's algorithm, rather than sort of propagating all the labels at once, you propagate one label at a time, okay? So for each class, we're going to start off by setting up a uniform distribution over all the instances in that class, all right? So that's the first step. And then we basically this is a random walk, but basically this is random walk with restart, okay? So this is the personalized PageRank algorithm using that vector, okay? So this is, but just, we could run exactly, you could approximate this with your APR algorithm. We're just starting with that seed vector, and we're going to do a random walk with reset on this graph, and then it gives everything a score, which is in some sense proximity to that seed vector, okay? So we do this random walk, we do that for every class, and then to classify things, we just see which, seed vector it's closest to. All right, so super simple idea. So the experiments I'm going to talk about, I think for this class, it's really just showing you that this simple algorithm does work pretty well. For the purpose of publishing it, we were trying to show this. So it turns out this algorithm is not completely novel. This was described a while back, and we came up with it independently. Of course, it's a very simple idea, so that's sort of what you'd expect. So we spent a lot of time looking at sort of variations of this. So we looked at basically a couple of questions that are related to how you choose the seeds when you're training. So if you're doing semi-supervised learning, you have a choice about which things you're going to label. So in our case, you can order things by either just randomly, which is kind of the normal thing, or you can choose some initial ordering. So we chose to choose an ordering of the data and then choose the label things in that ordering until you have at least k labels per class. Okay. So the orderings were by in degree or by page rank. And here's some experiments. So this is the function, the algorithm I just told you about, the harmonic fields, that label propagation algorithm. So the blue line is always that. You can see there's not a lot of difference for most of these things. These are the different seeding algorithms, and so don't try and line them up this way because they're not aligned that way. But this is using random seeds, which turns out to be worst. This is using the page rank seeds, which turns out to be best. These little squares are cases where there's a statistically significant difference. Okay, so after a while, they're mostly the same. Okay, if you use a reasonable amount of data, they're the same. But it starts out a little bit better with for the multi-rank walk algorithm. Here's some another data set where we get the same kind of pattern. These are not blog data sets, but citation data sets. And again, we're sort of seeing roughly the same thing. So particularly when you're looking at a relatively small number of examples, the best thing to do is use multi-rank walk. And usually the best thing to do is use the page rank. So this is a little bit clearer. This is using the page rank seeding. That's the green line, okay, in each of these cases. All right. And I guess the thing to look at here is that in the far left is the green sort of where you want to follow. So most of the time, the green is where you want to be, sort of at the far left. And actually, you get a pretty similar sort of behavioral. They're not quite as strong for the harmonic function algorithm. Okay. These are a couple of big overviews of the data. So here, every point is an experiment, and the red ones are with random seeding. The green ones are with page rank seedings. The blue ones are with link count seeding. Each one is a different data set, a different fraction of training data, right? And we're plotting these so the multi-rank walk score is on the left, is the y-axis, and the harmonic function score is on the x-axis. And so basically anything in this upper triangle, the multi-rank walk is doing better. So again, you can basically see it's mostly doing better. The cases it's doing, it's getting the most difference are cases where you're using random seeding, which is not as informative, or to a lesser extent link count seeding. All right, and this is the same thing. And here we're just looking at a different number of labels per class. Okay, so again, the green one is the most labels per class, and there's fewest differences here. And as you get to a small number of examples, then the multi-rank walk seems to be best. All right. So that's kind of the analysis. I'm going to skip this one, and this one, which is just parameter sensitivity things. But I'll show you this one because this is kind of cool. So this is showing a simple data set where these algorithms do something different, and it kind of clarifies what the difference is. So multi-rank walk, I said you're looking at proximity to the seeds, but it's really kind of a weird mix of proximity to the seeds and centrality in the graph. So if you have something that's very central in the graph, sort of the page rank part of the random walk with reset, we'll kind of focus on that. But since you go back to the seeds, of course, it'll kind of also reward things that are close to the seeds. So in the harmonic function, you don't really have that property. What you do is you have a hard constraint that anything that's close to the seed has to be labeled with that class. So here's a little graph, okay? The yellow nodes and the things that are marked as S are seeds, okay? So with the harmonic functions, there's this hub node which is very close to all these seeds, and the things that are hanging off that hub node are also clearly closer to the yellow seeds than the pink seeds, right? Here I've got something else where everything, we've got, again, the same sort of behavior, right? This guy's sort of only really close to the pink seeds, you know, it's much further away from the yellow seeds. So everything that's kind of close to that hub are also labeled, the majority class is the pink class, right? But right here, we've got this node where this guy is, you know, strongly known to be, you know, yellow. It's got all that, all the information kind of points to it being yellow. This guy is strongly known to be pink, right? And this guy sort of has to decide which one he's going to fall into, which one he's going to follow, okay? And the dynamics of the harmonic function is he's basically going to go with the guy that's closest to him. All right, this guy's going to be close to 1, but not really 1.0, right? This guy's going to be 1.0, so he's going to go with this, all right? So the multi-rank walk, it's a little bit different. Even though these are seeds, the fact that they're not central means they're not going to have the highest score, all right? So the multi-rank walk is going to pick the central node, so it's going to pick this thing kind of in the middle of the seeded area, and this thing in the middle of the seeded area. So these are the things it has most confidence in, right? It's not most confident in what you actually told it. It's confident in these things that are kind of strongly connected to what you told it. And, you know, as a consequence, when you have this sort of like, you know, fighting back and forth between something, so the fact that this is really close to this hub, which it has high confidence in, counts for a lot more. So that's an example of where it's different. We've actually used this in some later papers. So there's a series of papers over the last couple of years done with Lidong Bing, one of my postdocs. So the problem that Lidong and I were working with were similar to what we did in NEL. So you start off with some examples, like, you know, city examples like Pittsburgh, you know, San Francisco, Austin, and you look for mentions of those things in sentences. So here we're looking at entity pairs, like Rick Santorum lives in Pennsylvania, and we can find Rick Santorum in Pennsylvania in this sentence. So that suggests that this sentence might be an example of that relation. That's not really necessarily true, right? Just because he's a former senator, I mean, maybe he's actually, maybe this doesn't really mean that he lives in you know, Pennsylvania. So this could have been born in, which, you know, clearly is not necessarily true. So if you basically start with a knowledge base and use it to label sentences, you have noisy labels. But what seems to work is use the multi-rank walk label propagation method and use that to basically take the noisy example data and sort of clean it up, right? So the things that are match the knowledge base but are kind of outlier structurally will sort of get weighted down. The things that are, you know, sort of like central, you know, common things will get weighted up. And you can basically just learn a classifier from that distantly labeled data, and it works pretty well. So that's another, that's an application of this multi-rank walk stuff versus the harmonic functions. So the difference that we're exploiting here is that one of these basically treats the labels as you know, gold labels that have to be matched, a hard constraint, and the other one doesn't. So are there questions before I move on? All right. All right, I'm going to talk about a couple of other variants. Going from the harmonic fields to the multi-rank walk, you know, basically there's, you know, a slightly different algorithm chosen, but the big difference is in harmonic fields you have a hard constraint. that you have to match the seeds. In multi-rank walk, you don't. But in multi-rank walk, it's also not really clear exactly what you're doing. It's a simple algorithm, but there's not an optimization criteria that you're trying to maximize, right, or minimize, right? So there's no energy function that sort of corresponds to it. So Partha Talukdar did some work in the thesis, which kind of looked at this issue. So this is yet another name for the harmonic function algorithm, and this is Partha's notation, very similar. Okay, for every label, the predicted label should be kind of smooth along edges. So W are the edges. Okay, and there's a constraint that you have to match the seeds. Okay, and this is his notation for that. So the question is, can you sort of take this optimization algorithm and sort of relax it to have a soft match for the seeds? And certainly you can. So he proposed this variation. So S here is a diagonal matrix, which is kind of just true for the seeds. So this picks out the seed examples, and you can look at the difference between the predictions at those nodes and the seeds. So you want that to be small, okay? And small here means you're minimizing squared error, okay? And then there's another property here, which is the smoothness property. So that's the same as what we saw before, okay? So M is just a symmetric version of the weight matrix, a little kind of technical detail. And there's one other thing which is kind of useful to do. So remember, I said one piece of knowledge which turns out to be very useful empirically is to build in some knowledge about the prior distribution of labels. So you can build that in here, but you can basically say, well, I want the difference between your predicted labels and some prior distribution to be small, right? And these things have fudge factors that you can weight them up or down. And this is basically the optimization that Partha looked at. So it's a generalization of the harmonic function. So it has the same smoothness property, but it has a soft match instead of a hard match on the seeds. And of course, you can weight that up and down by filling with these parameters. And it also includes a prior over labels. So in the interest of time, I'll skip this part. So he has an argument that this is closely related to something called absorption, which is in turn closely related to the multi-rank walk. So absorption is basically sort of a twiddle on the multi-rank walk. So this is the basic idea. Another cool thing that Partha added was this notion of a dummy label. So there's some fixed number of classes that you have, but there's also something called a dummy label. Essentially, the dummy label is given with a small weight to everything in the graph. So it propagates everywhere, and it basically is a signal as to how far you are from any of the seeds. So if you're closer to the dummy label than you are to any of the seeds, then maybe none of the seeds really apply. So it basically gives you an option for sort of abstaining. Another thing you can do with that is you can use that. And so the main reason for doing that is when you have lots and lots of possible classes. So to do this minimization, I didn't talk too much about how you do this. So the harmonic function, there was an iterative algorithm which looked a little bit like PageRank. For the multi-rank walk, there was, in fact, random walk with reset, personalized PageRank. You can do this. I mean, kind of briefly, at this point, you kind of have the tools. You can do this, using an iterative parallel graph algorithm. So you can turn it into like a MapReduce process. Partha talks about how to do that using something called the Jacobi method, which is kind of fairly general. The details aren't really all that important. What's important is that you can basically do this in parallel if you want to. It's something where you can basically turn each iteration into a MapReduce pass, like we did when we were talking about PageRank. Or alternatively, you can do it with something like Pregel or one of these graph-based things. And that's in many ways more efficient because the graph sort of stays in memory. You don't have to write it out and read it in every time as you do in MapReduce. So these experiments are done using MapReduce. Some of these are big data sets, some of them aren't. Here's a widely used graph data set that just has like 3,000 instances. And this is a k-nearest neighbor graph, and it works pretty well. And these blue lines here are the old harmonic function algorithm. So you can see there's basically a big difference, again, when you get few labeled examples. And he's not comparing to multi-rank walk, but he's comparing to absorption, which elsewhere had been compared to multi-rank walk. So that's sort of fair. This is another semi-supervised learning task. That's a classification task with sentences, and you're classifying them by sentiment. Again, the same sort of story. So here's a really cool problem. And it basically, it shows you that there's sort of a lot of interesting things you can do with semi-supervised learning, things that don't necessarily look like learning problems. So I guess the short story here is this is a big graph with 2.3 million edges, and it worked pretty well. And Partha's algorithm worked better than the baselines. But what was the algorithm? What was the data set? So this is what the data set looked like. So you took two sources of information. So one is you took a big pile of tables, okay? So this was looking at HTML tables on the web. And I know there's at least one project that's looking at this sort of data. So the HTML tables on the web. And what you basically had was you had one node for every column in a web table, okay? And the other thing they looked at was looking at text patterns, like musicians such as Bob Dylan. So again, you have one node for every one of these patterns. So blank such as blank, you would look at the category thing. And you'll have again, you'll have one node for that category and then one node for each one of those instances. So what does that look like? So we've got some things like musician and singer, right? And they belong to, they're linked to these entities, okay? So we're going to take that graph and extend it. I guess I don't have the other slide. But we'll extend this. So in addition to these labels here from the text patterns, which sort of have some sort of meaning, there are also nodes which are just the IDs of table columns, and things that are in a table column together would also be linked together, right? So we end up with this big graph which basically says how things are connected, and we can treat each of these strings as a label. So we have thousands and thousands of labels, and we can propagate those all through the graph, all right? And we end up with this sort of structure. So there's like 9,000 classes, and all the entities in the graph are either class name strings or table nodes or entities. And here are some of the non-seeds that were found. So these are scientific journals, these are NFL players, these are book publishers, and it knows what these things are. So that's kind of cool. Okay, so this is another kind of interesting application of this kind of label propagation. So I'm going to talk now for just a few minutes about a couple of recent papers that take this same framework and kind of push it a little bit further. And this is, partly just to give you guys a little bit more background and kind of what's going on in the research community, partly to help you understand what the limitations of these techniques are. So from the computational perspective, these techniques seem really fast, okay? So there's no learning, there's no parameter testing, there's no tuning, there's no iteration of the model that happens, right? You just basically load in the data in a big graph, right? Iterate over the graph a couple times, you're done, bam, right? So it's linear in the number of edges. You know, I told you harmonic function just iterates like 10 times. So the whole process is like 10 times the number of edges in the graph. It's linear in the number of labels, right? So in the, the MAD algorithm and the harmonic function algorithm, basically you're pushing through all the labels at once, right? And it's just sort of linear in the number of labels each time you do a propagation stage. So linear in the number of edges in the graph, linear in the number of labels. I mean, what more could you want? I mean, this is a scalable algorithm, right? Oh, I know what else you could want. You could parallelize it, right? So it's an operation on a graph, and you know, lo and behold, there are all these smart people like Carlos Guestrin and the Spark people, you know, Joey Gonzalez. They've been working for the last few years to build these nice platforms for dealing with iterative algorithms on graphs efficiently. So it's a beautifully scalable algorithm, okay? So we're done, right? Total success. All right, well, here are some things that people have done sort of after we were done, okay? So it's linear in the number of edges and the number of labels being propagated, okay? So can you do anything better than that? So, so in practice, what happens with this, if you're not working on with like a fancy, you know, graph method like GraphLab or Pregel, what happens is, as the graph gets bigger, you load it into memory to do your propagation, and you run out of memory. Okay, so at some point it just gets too big because you have too many labels that are being pushed around. So what can you do? So one thing you can do is, instead of keeping the labels in just a vector, you can use a count-min sketch. So remember, a count-min sketch looks like this, right? So what you're doing is you're keeping a running score over some property, like maybe a class label, and then some count that gets associated with that, all right? So whenever I'm looking at a neighbor, I look at sort of like its class labels, and I increment some count associated with those. That's what that kind of happens when I'm computing a running average. Instead of storing those all explicitly in a big sparse vector, I'm storing them in this kind of dense, low memory, but moderate error sort of data structure. So I'm using this randomized algorithm that will store that big vector compactly. One thing that's really nice about this is that if I have two of these sketches, I can combine them very easily. So if I've got, let's say, one sketch, which is all the labels that propagated to node I, another sketch which is all the labels that propagate to node J, right? And node K is connected to I and J. So I can basically just take the sketch for I and the sketch for J and just add them up, right? Just like component-wise as matrices. And I'll get a summation of those things, right? And it's just exactly the sum of the underlying vectors. That basically means that in the label propagation algorithm, you can replace all the steps where you're doing label propagation with cases where you're just adding up these, computing weighted sums of these sketches. So it turns out that algorithm is pretty efficient. So now basically you have something which is linear in the number of edges, but not the number of labels being propagated, just the sketch size, okay? And you can do this because you can, take a vector v and vector w. You can do a weighted sum of those and get the sketch for that. And you don't need these vectors, right? You can just take the sketch for v and the sketch for w and compute the weighted sum of those. All right. So the other reason this works is that sketches are really good at storing skewed distribution. So if there are only a few elements in the sparse vector that contribute to its mass, then the sketch should be able to store them compactly. And this is often the case. So if you're looking at big graphs, they often have this sort of community structure. So there's sort of these small-ish, densely connected areas. The weights you propagate from subcommunity to subcommunity are pretty small. The weights within a subcommunity are pretty large. So typically, you've got a few big weights and a bunch of really small ones. So that's a nice property. This is, so if this was a straight line, this would mean you sort of had a Zipf's law for weights. In fact, it's stronger than that, right? So it zips for a while, and then it sort of just kind of plummets. And here's another data set. Again, we're looking at sort of the score of these things. So these are some big propagation problems. So these are, millions of edges, millions of nodes, millions of labels, okay? And we take that, we compress it down to a relatively small number of dimensions in a sketch. So this is a 55 by 17 sketch, so just a few hundred components. And we're able to get a pretty good compression for, I guess this is actually a moderate sized problem, 200 labels and about 1 million edges. But you get a really big compression for other data sets. So this is one that's sort of about as big as we could do on the machine we had at the time, which was like 200 gigabytes. And without the sketch, it basically just doesn't fit. All right. So that was from 2 years ago. So since then, Partha kind of left CMU. He's now a professor at IIS in India. I've gone on to work with other things. So last year, there was a paper, or I guess last spring, I guess, there was a paper by some guys at Google. So Keeming was an intern, I believe. So they had basically a very similar system to the one that Partha and I built. So a couple of differences. These objective functions are maybe starting to look a little bit familiar to you, but it's basically the same objective function as in MAD. You have a soft match to the seeds. You have the same smoothness, quadratic constraint on smoothness. You have a particular label regularizer, so you're regularizing things close to a uniform distribution, and that's actually kind of important for them. And then you normalize, which is not usually in the objective function, but something we always do. So what do they do? So one thing they do is they did parallelize this, and the way they parallelized it is they just implemented it in Pregel. Okay. The other thing is they used sketches, but they used another strategy for sketching. So this is called a streaming approach, and this is I've only looked at this paper recently, so I haven't kind of gone through the details of the math behind it. But the basic idea is pretty simple. You're looking at a series of updates, so you've got maybe many dozens or hundreds or thousands of updates for neighbors. So these are for large graphs. So you're trying to figure out whether those updates are going to be important or not, whether it's basically going to be a big value that you should keep or it's going to be a small value. Okay, so the essential idea is you're going to treat this as a stream of independent events, and what you're going to do as what you're going to maintain as you go through the stream is basically a label ID, a score for that label, okay, and then some sort of error bar, okay, the stream itself is going to be broken into sections. So maybe you've got 1,000 updates. You're going to break them into sections of 100, all right? And after 100, you're going to look at, the statistics that you've computed so far and say, well, does it look like this score is actually that different from, my kind of default score, which would be uniform, right? If it's not, you just throw it away. So you sparsify by basically, you give yourself a little bit of time to be convinced that that weight is significant. And if you're not convinced at that point, then you truncate it, okay? So it's a simple idea. The math behind it's a little bit complicated, but the basic idea is pretty simple. So what you're basically doing is every so often, while you're streaming through your updates to a label distribution, you sparsify. Okay, this seems to work really well. I actually don't have the accuracy numbers, but in terms of accuracy, it does better than MAD. It certainly is better than Meta with a sketch, which does seem to hurt its performance a bit. It also seems to scale really well with a number of labels. So, again, this is going from, I guess, so order 100 labels to like order, several hundred thousand labels, and there's not really much of a change in the size. So dist is the distributed version of Expander, okay? And then this is runtime over the number of nodes in the graph. So, it does get slow as you get a big enough graph, okay? But when you parallelize, it can handle extremely big graphs pretty efficiently. Okay. So any questions? Okay. So I'm going to end a little bit early here, I guess. And we'll see you guys on Thursday.